I want you to picture um, something incredibly mundane, something you've probably done like 100 times without even giving it a second thought.
Oh, absolutely. The mundane stuff is usually where the best science hides. Right.
Right. So you're in a dark room, maybe the power just went out during a storm, or you're looking for something under the bed, and you switch on an electric flashlight.
Yeah, just a regular flashlight. Nothing fancy.
Exactly. You point it at the wall, and maybe you hold your hand up in front of the beam to make a shadow puppet. You see the bright light hitting the wall. You see the dark shadow cast by your hand.
And right between the two, you see that slightly blurry, fuzzy gray edge.
The penumbra.
Yes, the penumbra. Now, what if I told you that that slightly blurry edge of that shadow, that totally mundane, easily ignored little gray zone, is actually airtight physical scientific proof of the existence of parallel universes?
I mean, it sounds like pure science fiction when you say it like that.
It really does. Or, maybe a misinterpretation of a mathematical quirk. But it is, in reality, the inescapable conclusion of some of the most rigorous, heavily tested physics ever conducted by human beings.
Which is just staggering to me.
When we look at that fuzzy shadow, our common sense tells us to expect simple geometry. Light traveling in straight lines being blocked by an object.
Like simple geometry.
But what we are actually witnessing right there in our living room is a physical interaction with realities that we cannot directly see.
That is it's staggering. And that mind-bending reality is exactly what we're going to unpack today. Welcome to this deep dive.
It's going to be a fun one.
Our mission today is to explore a framework laid out by the visionary physicist David Deutsch in his landmark book, The Fabric of Reality.
A fantastic book.
It really is. And our goal here isn't just to memorize some quirky quantum physics facts to sound smart at parties. We are going to look at how four seemingly totally unrelated threads of science actually braid together.
The four strands.
Yes, the four strands. We're talking about quantum physics, the theory of knowledge, or epistemology, the theory of computation, and the theory of evolution. And when these four strands braid together, Deutsch argues they form a true, unified theory of everything.
Which is quite a massive departure from how we usually use that phrase in science.
How so?
Well, usually when theoretical physicists talk about a theory of everything, they are talking about a mathematical formula. They mean a single elegant equation that unifies gravity, electromagnetism, and the strong and weak nuclear forces.
Like putting all the fundamental forces on one t-shirt.
Exactly. It is a purely reductive pursuit. They're trying to find the ultimate tiny building blocks of matter. But Deutsch is arguing for something far more profound and expansive.
So it's not just about subatomic particles.
No, not at all. He is proposing a framework that explains not just subatomic particles and gravity, but life, thought, problem solving, and computation.
And to you listening right now, if you ever look at the news or read scientific journals, and you sometimes feel completely overwhelmed by the sheer volume of fragmented facts in the world.
Which is easy to feel these days.
Oh, absolutely. If it feels like every single day there's a new subspecialty, a new subatomic particle, a new piece of contradictory data that just makes the universe feel increasingly chaotic and impossible to grasp, this deep dive is your antidote.
That's a great way to frame it.
Because the beauty of what we are exploring today is that deepening our foundational theories actually simplifies the universe. It proves that reality is, at its very core, inherently comprehensible.
You don't have to be a mathematical genius to understand reality. You just need to understand how these four strands connect.
I am beyond excited to get into this because these concepts completely altered how I see the world.
It is an absolute thrill to synthesize this material because it forces us to reconsider the very foundation of what we consider real. And to do that effectively, to really build this framework, we actually cannot start with the parallel universes or the quantum physics.
Wait, really? Why not?
Because if we start there, it just sounds like magic. We have to start with a much more grounded philosophical question. How do we know what we know? We have to examine the purpose of science itself.
Right. Okay, so we're starting with the epistemology strand, the theory of knowledge.
Yeah.
Because before we can talk about a multiverse, we have to talk about why we even trust the scientific method that eventually leads us to the multiverse.
Exactly.
So let me pose the basic question. Why do we do science? Like if you ask the average person on the street, I think almost everyone would say, we do science to predict what's going to happen.
Yes, to predict outcomes.
Right. You figure out the laws of physics, so you know exactly where the cannonball is going to land or what weather is coming tomorrow. Prediction is the goal.
And that is a very common, very intuitive view. But it is also a deeply flawed view of science, known in philosophical circles as instrumentalism.
Instrumentalism. Okay, break that down for me.
Instrumentalism claims that a scientific theory is nothing more than an instrument, a tool for making predictions. That the only thing that matters is the math that tells us the outcome of an experiment.
So just the math,
Yeah.
nothing else.
To a strict instrumentalist, the explanation, the why or the how behind the prediction, the story of what is physically happening behind the scenes is totally irrelevant.
Wow.
They view explanations as just psychological props, comforting stories we tell ourselves to feel better about the math. There's a famous phrase associated with this view in quantum mechanics, actually, shut up and calculate.
Okay, but I want to push back on that a little because isn't prediction essentially the ultimate test?
In what sense?
Like, if my math perfectly predicts every single time that a bridge will hold a certain amount of weight, why does it matter what philosophical story I tell myself about the atoms in the steel?
Yeah.
The bridge works.
It matters entirely if you want to make progress. David Deutsch illustrates exactly why prediction is not enough with a rather brilliant thought experiment.
I love his thought experiments. Let's hear it.
Imagine that tomorrow, an incredibly advanced alien race lands on Earth. And they don't conquer us. Instead, they hand us a gift. A super advanced piece of technology that we'll call an oracle.
Okay, an oracle.
This oracle is essentially a black box supercomputer, and it can perfectly predict the outcome of absolutely any physical experiment we ask it about.
Anything at all.
Anything. You type in the starting conditions, you press enter, and it tells you exactly what the result will be.
Wow. Okay, that would be wild.
Now, if the instrumentalist view is correct, if science is exclusively about predicting things, then the moment the aliens hand us this oracle, science is officially finished.
Because we have the ultimate prediction machine.
Correct. We have achieved the ultimate goal. We can shut down every university, close every laboratory, and all of the scientists can pack up and go on permanent vacations.
Sign me up for that vacation. But I feel like there's a catch.
There is a massive catch. Let us think about how we would actually use this oracle in reality. Suppose we want to build a revolutionary new interstellar spaceship to go visit these aliens.
Okay, we want to go say thanks.
Right. We spend years designing it, drafting the blueprints, inventing new alloys. We feed all these blueprints and schematics into the oracle, and we ask it what will happen on the maiden test flight of this spaceship.
And what does it say?
The oracle computes for a millisecond and outputs its perfect prediction. The spaceship will violently explode on the launch pad.
Oh, man. Well, okay. That is incredibly useful information.
Mm-hmm.
We just saved billions of dollars and probably the lives of our astronauts. We predicted the disaster.
We did predict the disaster, but think about our next step. What do we do now?
We fixed the ship.
The oracle told us what will happen, but it gave us absolutely zero information about why it will happen.
I see the trap.
Was it a fuel leak in the propulsion system? Was it a structural failure in the hull because of the new alloy? Was it a tiny software glitch in the navigation computer?
The oracle provides no explanation, so we have no idea what to fix.
Exactly. How do we fix the spaceship? We cannot just randomly change lines of code or swap out metals blindly and keep feeding it back into the oracle hoping for a different result. That would take an eternity.
Right. We still have to use human creativity. We still have to understand how the engines actually work, how the materials handle thermal stress, and how the software processes data to even begin forming a hypothesis about what went wrong.
So the oracle just replaces the physical testing phase. It doesn't replace the science.
The science is the understanding. If we just have predictions, we are stuck. We can't build a better ship without understanding the flaw in the first one.
A prediction, even a mathematically perfect, universally infallible prediction from an alien supercomputer, is simply no substitute for an explanation.
That totally shifts how I view the scientific method. Understanding is entirely about the why, not just the what. Explanation is the actual engine that drives human progress. We want to know the inner workings of reality.
The true purpose of science is to explain the world. Passing experimental tests, making accurate predictions. Those are just the tools we use to check if our explanations are actually good. They are the quality control mechanism, not the end product.
Right. I'm completely with you on the necessity of explanations, but let me play devil's advocate here.
Please do.
Even if we agree we need explanations, doesn't physics eventually just explain absolutely everything by reducing it to its smallest parts?
You were referring to reductionism?
Right, the reductionist view. Like, if we want the ultimate, deepest explanation of that spaceship or a planet or human behavior, don't we just zoom in and in until we are looking at atoms bouncing around. You figure out the fundamental particles, you write the equation for how they bounce, and boom, you have explained the universe.
That is precisely the reductionist hierarchy, yes.
Yeah.
It is deeply ingrained in our modern scientific culture. It places subatomic physics at the absolute base, the fundamental bedrock of all reality.
And everything else sits on top of it.
And it views everything else, chemistry, biology, psychology, economics, history, as just derivative, high-level summaries of those bouncing atoms.
It suggests that if you had a big enough computer, you could deduce the French Revolution purely from the laws of quantum mechanics.
But Deutsch argues forcefully that this hierarchical structure of scientific explanation is completely wrong.
And this is where the book introduces an absolutely fascinating, grounded example to tear down that reductionist tower. I want to talk about the copper nose.
Ah, yes. Let us consider a very specific physical object. Picture a single specific copper atom resting exactly on the tip of the nose of the bronze statue of Winston Churchill, which stands in Parliament Square in London.
Okay, got its picture.
And we ask a very simple scientific question. Why is that specific copper atom there?
Okay, so if I take the ultimate reductionist view, I would say, I can answer that. I would consult a theoretical supercomputer that knows the position and momentum of every particle in the universe since the Big Bang.
And what would it tell you?
And that supercomputer would trace that specific copper atom's physical trajectory. It would map how it was forged in the heart of a dying star, how it was expelled in a supernova, how it drifted through space to become part of the forming Earth.
A very detailed history.
Right, it would trace its movement through geological shifts into a copper vein, its extraction by miners, its journey through a smelter, into a sculptor's studio, into a bronze alloy, and finally, precisely into the mold that forms the tip of that statue's nose.
And the math would be flawless.
The physics equation would predict perfectly, through gravity and momentum and electromagnetism, that the atom would end up exactly there. So, didn't I just explain it? Physics put it there.
You described its path with perfect accuracy, but did that incredibly complex particle-by-particle history actually explain why the atom is there?
I mean, technically yes, but practically?
If I ask you, why is there a copper atom in Parliament Square, and you give me a multi-billion-year printout of atomic coordinates, have you actually answered the spirit of the question?
No, it tells me nothing about the context.
Exactly. It misses the entire point of the reality we live in. To actually understand why that copper atom is resting on that specific geographical spot on Earth, subatomic physics is utterly useless.
So what is the actual explanation?
To explain its presence, you need to rely on emergent, high-level concepts. You need to understand abstract ideas like leadership. You need to understand tradition. You need to understand the historical reality of the Second World War.
Oh, wow.
Winston Churchill led the Allied forces. Human beings have a sociological tradition of honoring such leaders with statues in significant public squares. Statues of this nature are traditionally cast in bronze, and bronze is an alloy that contains copper. That is the true explanation for why the atom is there.
That is brilliant, because the reductionist supercomputer wouldn't know what a Churchill is or what a war is. It just sees particles. But the war and the leadership are the actual causes of the statue being built.
Exactly.
So what you're saying is those high-level concepts, ideas, history, human motives, they aren't just convenient shorthand that we use because our brains are too small to do the physics math.
They are emergent phenomena that have genuine causal power in the physical universe. They are absolutely necessary to explain the physical arrangement of matter.
That is mind-bending.
You cannot deduce the existence of a Winston Churchill statue purely from the laws of quantum mechanics, no matter how powerful your computer is. There is no lower-level explanation that suffices. The concept of leadership literally moved that copper atom to that specific GPS coordinate.
So, tying this back to our theory of everything, it means that a true theory of reality cannot just be a math equation about quarks and electrons. High-level concepts, life, thought, computation, knowledge are just as fundamental, just as physically real as subatomic particles.
The fabric of reality isn't just a bottom-up grid of particles, it's interwoven with these emergent truths. The central takeaway here is that the most fundamental theories in science are not necessarily the ones referring to the smallest scale of size.
They are the ones with the deepest explanations.
Yes, the most fundamental theories are the ones that contain the deepest, most far-reaching explanations.
Okay, I love this focus on the best explanation. But if we are building our entire worldview on, well, just accepting the best available explanation, we run headfirst into a very old, very stubborn philosophical wall. I'm talking about the problem of induction.
Ah, yes. David Hume's famous critique.
This is the panic-inducing idea that just because the sun rose yesterday and the day before that, and every day for billions of years, we actually have no absolute, logical, mathematical proof that it will rise tomorrow.
Which has haunted philosophers for centuries. Inductivism is the standard idea that we can justify general scientific theories about the future based on repeated observations in the past.
Right. We drop a rock 1,000 times, it falls 1,000 times, so we induce the rule, rock fall.
But logically, as Hume pointed out, no matter how many times you observe a phenomenon, the mere repetition does not logically guarantee it will happen again. There is no deductive proof that the future must resemble the past.
It's a scary thought.
Because of this, many philosophers have agonizingly concluded that science is fundamentally unjustified, that it rests on a massive leap of faith, and that all our theories are ultimately just highly educated guesses.
And Deutsch completely rejects this panic. He uses a wonderful dialogue in the book to illustrate how absurd the problem of induction really is when you apply it to reality.
He sets a scene at the very top of the Eiffel Tower.
Right. You have a philosopher, let's call him the crypto-inductivist, and he is desperately trying to convince another person, let's call him the floater, not to jump off the edge.
It perfectly distills the conflict.
So the floater is standing on the ledge, and he says to the philosopher, I have a new theory. I believe that today the laws of physics are going to take a break just for me, and gravity won't apply. I will just gently float down to the ground.
And the philosopher, panicking, says, you can't jump. Every single time anyone has jumped off a high place in the past, they plummeted and died.
And the floater just calmly replies, sure, I agree with your data. That was the past. But I'm talking about the future. My theory applies to today. Logically prove to me that I won't float.
And the deeply uncomfortable truth of philosophy is that the philosopher cannot deductively prove the floater won't float.
Because there's no logical contradiction.
Exactly. There is no strict logical contradiction in the idea of gravity suddenly switching off at 3 p.m. on a Tuesday for one specific person. Logic alone allows for it.
Wait, why don't we jump? If we can't prove gravity will work tomorrow, aren't we just guessing?
It feels like a guess to some.
Like, why doesn't the philosopher just shrug and say, well, it's a 50-50 shot, go for it? If we aren't using past observation to guarantee the future, aren't we making a blind leap of faith every time we step out of bed expecting the floor to be there? I'm going to push you on this because it feels like we do rely on the past.
We feel like we do, but we actually do not rely on past observations to justify our actions. We rely on our best explanatory theories.
Okay, explain the difference.
We do not jump off the tower because the theory of gravity, specifically Einstein's general relativity, explains why objects fall. It provides a deep structural explanation of the curvature of space-time created by mass.
It gives us a mechanism.
Now let us evaluate the floater's theory. To assume that he will float today requires postulating a massive, entirely unexplained anomaly.
A magical floating force.
It requires assuming some magical, invisible upward force that acts only on him, only at this specific time, and it provides absolutely no mechanism or reason for why this would happen.
It's just a terrible, terrible explanation.
Exactly. We choose to rely on the theory of gravity not because it has been proven by a million past dropped apples. We rely on it because it is currently the best, most coherent, most tested explanation of how mass interacts in the universe, and there are currently no valid rival explanations that account for the phenomena better.
So the floater's theory is just worse.
A theory that postulates a massive, unexplained anomaly like floating off the Eiffel Tower is, by definition, a significantly worse explanation than one that doesn't.
So we don't need absolute mathematical certainty about the future.
We do not. The quest for absolute certainty is a phantom. Science is not about certainty. It is about the continuous improvement of explanations. We simply need to follow the best explanation available to us at any given time.
That is such a liberating way to look at human knowledge. We are not prisoners, blindly trusting past data tallies. We are active evaluators of explanations.
And the core rule of this deep dive, the core rule of understanding the fabric of reality, is that we must trust our best explanations.
And we must follow them logically, no matter how weird or counterintuitive the destination might be.
And establishing that principle is the perfect, necessary bridge to our next strand. Because if we truly commit to taking our best explanations seriously, if we refuse to just shut up and calculate, we are forced to accept something truly astonishing about the physical world.
Which brings us right back to that dark room, the flashlight, and the shadow puppet. We've established that we have to follow the explanation. So let's follow the light.
Let us design a thought experiment regarding that flashlight beam to understand how light truly operates.
Okay.
If you stand in an open field at night and point a flashlight into the vast empty space, the light spreads out. It illuminates a cone of space.
Right.
And as you move further and further away from the source, the light appears to get dimmer. This is intuitive. The same amount of light energy is simply spreading over a much larger surface area.
It makes total sense. I always visualize it like spreading butter over a piece of toast.
A very apt visualization.
If you have one pat of butter and a small piece of toast, it's thick. If you spread that same pat of butter over a piece of toast the size of a dining table, the butter gets incredibly thin. So the light is just getting stretched thinner and thinner.
That is the classical wave view of light. But the vital question is, can it get infinitely thin? If you just keep backing away forever, millions of miles into deep space, does the light just get infinitesimally dim but remain a continuous, unbroken wash of faint illumination?
To figure this out, we can't just use our human eyes. They aren't sensitive enough. We need a really good observer.
Deutsch suggests using a frog.
Frogs happen to have highly sensitive eyes, capable of detecting incredibly faint light. So we strap our frog into a little spacesuit, put it in a spaceship, and move it millions of miles away from our flashlight.
At a distance of, say, 100 million kilometers, the frog looks back toward the source of the flashlight. If light were like butter, if it could be spread infinitely thin, the frog would just see a remarkably dim, continuous glow.
But that's not what happens, is it?
Oh.
The frog doesn't see a continuous dim glow at all. It sees distinct, equally bright flickers. It sees a flash, then a long pause, then another flash, then another pause.
And those flickers might be hours or even days apart, depending on the distance.
But here's the crucial part. When a flicker does happen, that tiny flash is just as bright to the frog's eye as a flicker you'd see if you were much closer.
This represents the discovery of quantization. It is the realization that light is not infinitely malleable. It is not a continuous fluid. It comes in irreducible, discrete, indivisible packets of energy called photons.
Photons.
When the flashlight beam spreads out over millions of miles, the individual photons do not get dimmer or thinner. They simply get further apart from one another. The empty space between the photons grows. That is why the frog sees discrete flashes separated by time.
Okay, so light is a stream of distinct particles, tiny little bullets of light. Got it. But here is where the simple act of casting a shadow completely shatters our common sense understanding of reality.
To understand the shadow penumbra, we need to walk through an escalating physics experiment. Let's start with the famous double-slit experiment.
Walk me through it.
We set up a very simple apparatus. We have a light source. A laser is best because it provides pure single-color light. In front of the laser, we place an opaque physical barrier.
Like a wall.
Exactly. In this barrier, we cut two incredibly tiny parallel vertical slits very close together. And some distance behind the barrier, we place a screen to catch the light.
Now, if light was strictly a stream of particles, like firing tiny billiard balls from a machine gun at a steel plate with two slits in it, you would expect the balls to either bounce off the plate or travel straight through the two slits and hit the back screen, creating two bright vertical lines. Just a simple shadow geometry.
But that doesn't happen.
It does not.
Because light, while composed of particle-like photons, also behaves as a wave. As the light passes through the two tiny slits, it spreads out on the other side, like water waves passing through a breakwater.
So they interact.
The waves from the left slit overlap and interact with the waves from the right slit. Where two wave crests meet, they amplify each other, creating a bright band. Where a crest meets a trough, they cancel each other out, creating a dark band.
So instead of two bright lines on the screen, you get a whole series of alternating bright, dark stripes spreading out across the screen. An interference pattern?
Exactly. This is standard, well-documented quantum mechanics. The photons are acting like waves and interfering with each other. But now, Deutsch asks us to escalate the experiment.
This is where it gets crazy.
We take our barrier, and we cut two more slits into it, parallel to the first two. We now have a barrier with 4 open slits.
Okay, let's think about this logically. We have a light source, and we have opened more doors for the light to pass through. So intuitively, more light should hit the screen. The room should be brighter overall, and maybe we get a slightly more complicated striped interference pattern.
We turn the laser back on, we look at the screen, but we are going to focus our attention on one very specific spot on that screen. Let us call it point X.
Point X.
When only 2 slits were open, point X was sitting squarely in the middle of a brightly illuminated band. Photons were consistently hitting point X. Now, with 4 slits open, we examine point X again.
And it's dark. Point X goes completely, inexplicably dark.
It receives almost no photons.
Okay, I have to stop here because this is the part that always breaks my brain. Opening more doors in a wall makes a spot on the opposite wall darker. How can adding more light possibly create darkness?
It defies everyday logic.
The light from the first 2 slits was hitting point X perfectly fine a minute ago. Something must be physically stopping that light from reaching point X now that the new slits are open. What is going on? Did the photon split into pieces, go through all 4 slits, and then somehow crash into itself and cancel itself out?
That is a very reasonable logical hypothesis. It is the first thing physicists assumed, but we can test it.
How?
We can lower the power of our laser so drastically that it is firing only one single photon through the apparatus at a time. One flash, pause, one flash. We can also place highly sensitive detectors right at the slits to see where the photon goes.
And what do we see?
When we run the single photon test, the detector only ever goes off at one slit at a time. We never detect half a photon. We never see a photon split into 4. It remains a singular, indivisible lump of energy.
Okay, so the photon absolutely does not split. Then what else could it be? Maybe the photons are bouncing off each other. Like a photon goes through slit number 3, and it acts like a billiard ball, smashing into a photon going through slit number 1 and knocking it away from its original path toward point X.
Another excellent guess. But remember, the parameters of our new test, we are firing only one photon at a time. There is only one single photon in the entire apparatus.
Oh, right.
There are no other visible photons in flight for it to bounce off of. Yet, even when we fire them one by one, hour after hour, and track where they land, they gradually build up the exact same 4-slit interference pattern. Point X remains stubbornly dark.
So consider the mystery. A single, indivisible photon passing through one slit is being physically deflected away from point X. And the only reason it is being deflected is because we opened other slits that the photon did not pass through. So if the photon doesn't split into pieces, and it is not hitting other visible photons, what the hell is it hitting? What is physically knocking the tangible photon off its straight-line path? Because it can't be nothing.
It cannot be nothing. We must apply what Deutsch calls Dr. Johnson's criterion, the idea that if something kicks back at you, it physically exists.
It has to be real.
Something real is coming through those newly opened slits to physically interfere with our photon. And because we have rigorously ruled out all other possibilities, the inescapable logical conclusion is that there are invisible particles pouring through the other slits.
Deutsch terms them shadow photons.
Yes, shadow photons.
Shadow photons. This is where the epistemology we talked about earlier is so important. We have to follow the explanation. We can't just say, well, the math says point X goes dark, so shut up and calculate.
Precisely. The explanation demands that something physical is deflecting our light.
So these shadow photons, they have all the properties of regular photons. They follow the same laws of physics. They travel at the speed of light. They pass right through the open slits. They bounce off the opaque parts of the barrier.
But we absolutely cannot see them.
Right. The only way they interact with our universe is by interfering with the path of their tangible counterparts.
And we can mathematically extrapolate the sheer scale of this phenomenon. If we cut holes anywhere in the barrier, in any configuration, the interference pattern on the screen changes accordingly.
So they are everywhere.
This implies that these invisible shadow photons are not just isolated anomalies, they are pouring through the barrier everywhere we look, in staggering numbers. By calculating the number of possible hole locations on a standard screen required to explain the interference, the math dictates a jaw-dropping ratio.
What's the ratio?
For every single tangible photon we can see in our universe, there must be at least 1 trillion shadow photons accompanying it.
1 trillion. For every single particle of light. And it's not just photons, is it?
No, it is not. Quantum theory predicts, and experiments have confirmed, that this interference occurs for every sort of particle. Electrons interfere. Neutrons interfere. Entire atoms interfere with invisible counterparts.
Which means...
This implies shadow barriers, shadow laboratories, shadow scientists conducting the experiments.
So these aren't just phantom particles floating around aimlessly in a void. If there is a shadow barrier stopping the shadow photons, there must be a shadow Earth holding up the shadow barrier. There must be shadow people.
It scales all the way up.
Reality is a massively parallel multiverse. And the universe we see, the tangible universe we interact with every day, is just one impossibly thin slice of a structure that is trillions of times larger.
It is a profound, earth-shattering paradigm shift, and it happens simply by demanding a rational explanation for the shape of a shadow.
Because if we refuse the instrumentalist cop-out, if we refuse to just say it behaves as if something interfered with it, but don't ask what, and we actually demand a physical explanation, the existence of the multiverse is the only explanation that works.
The competing Copenhagen interpretation of quantum mechanics tries to claim the photon is a wave of probabilities that magically collapses into a particle when we look at it. But as Deutsch points out, that explains nothing.
What causes the collapse? When does it happen?
It is a terrible explanation. The multiverse is the only coherent explanation that doesn't rely on magic.
Okay, let's unpack this reality for a second. If there are trillions of parallel universes all around us right now sharing the same physical space, are they just floating out there entirely separate from us like separate bubbles? Or do they interact with us in a meaningful way beyond just making a spot on a wall dark?
This is a crucial transition.
Which brings us to our third strand, quantum computation and the labor of parallel universes. This is where we transition from theoretical physics into the theory of computation.
To understand how deeply intertwined these universes are, we have to look at the sheer amount of mathematical processing required to figure out where a single photon lands on a screen in a complex environment.
Right, because 4 slits is one thing. But let's say we don't have 4 slits. Let's say we have a barrier with 1,000 microscopic holes in it.
To calculate the final resting place of a single photon going through a barrier with 1,000 holes, the laws of quantum mechanics require us to track the mutual interference effects of 1,000 parallel universe versions of that photon.
1,000 versions.
We have to mathematically calculate 1,000 different paths, and then calculate how all of those paths cross, overlap, amplify, and cancel each other out to determine if the tangible photon hits one specific point.
And that's just for one photon. If we were trying to simulate an interaction between 2 particles, each with 1,000 paths, that's 1,000,000 different states we have to track simultaneously. 3 interacting particles is 1,000,000,000 states. The math scales exponentially.
Exactly. The complexity explodes. For a classical computer, the kind sitting on your desk, or even the most powerful supercomputers currently operating on Earth, simulating even a relatively simple quantum system of a few dozen interacting particles is what computer scientists formally term intractable.
Intractable, meaning it's practically impossible.
The computational resources and the time required increase so exponentially that it becomes physically impossible. A classical computer would take longer than the current age of the universe to simulate a simple molecular interaction.
It would take billions of years to do the math. But, and here's the kicker, nature does it instantly. When we actually shine a laser through 1,000 holes in a piece of metal, the photon hits the screen immediately.
Nature doesn't need to buffer.
Nature isn't buffering. Nature is already doing this insanely complex, intractable math in real time.
That was the brilliant realization of the physicist Richard Feynman. He saw that the intractability of calculating quantum environments wasn't just an annoying obstacle for physicists, it was an unprecedented opportunity.
How so?
If nature can process information at a scale that dwarfs our best supercomputers simply by letting a photon pass through a screen, why not harness that underlying process? Why not use nature itself as the computer?
Thus, the birth of the quantum computer. Instead of trying to simulate the multiverse with a classical one-universe computer, we build a machine that actually uses the multiverse to do the heavy lifting.
Precisely. We construct a physical device where we can cleverly encode our difficult mathematical problem into the initial state of a quantum system, perhaps by arranging the configuration of mirrors in an interferometer or manipulating the spin states of individual atoms.
And then
we simply let the natural process of quantum interference occur. We let the universes interact.
And this isn't just some abstract whiteboard theory. This concept has massive world-altering implications for the modern world, specifically in cryptography. Let's talk about Shor's algorithm, because this is where the theoretical multiverse meets the real world.
It is the perfect real-world application. Right now, global communications, secure financial transactions, national security secrets, they're all secured by public key cryptography, specifically the RSA crypto system.
And how does that work?
RSA relies entirely on a mathematical asymmetry. It is incredibly easy to multiply 2 massive prime numbers together to get a huge result, but it is computationally intractable to take that massive resulting number and reverse engineer it to find the 2 original prime factors.
To make that concrete, if I give you the number 15, you can instantly tell me the prime factors of 3 and 5. It's easy. But if I give you a number that is 250 digits long and ask you to find the two prime numbers that multiply to create it, a classical computer would have to check essentially every possible combination one by one.
Would take forever.
It would literally take longer than the age of the universe to crack it. The problem is practically unsolvable.
That was true until a mathematician named Peter Shor discovered an algorithm designed specifically for a quantum computer that can factorize those massive numbers efficiently and quickly.
Here is how I like to visualize the difference between classical and quantum computing. Imagine the problem is like being lost in a massive labyrinth.
Okay, a maze.
A classical computer tries to find the exit by running down one path. If it hits a dead end, it walks all the way back to the start, crosses that path off its list, and tries the next one. It checks them sequentially, one by one. It takes forever.
Every linear approach.
But a quantum computer sends a million versions of you down every single path simultaneously in a million parallel universes. And the version of you who finds the exit shouts back to you, telling you the way out.
That is an excellent visualization for conveying the sheer scale of parallel processing, though to be completely scientifically accurate, we must be precise about the mechanism.
Right.
The version that finds the exit doesn't literally shout back because, as we established with the shadow photons, universes can only interact via the physics of interference.
Right, they can't send a text message or a radio signal across the multiverse.
Exactly. What Shor's algorithm actually does is orchestrate an incredibly clever, beautifully designed interference pattern. The algorithm is structured so that the computational paths leading to the wrong answers, the incorrect prime factors, are made to interfere with each other destructively.
Okay, I want to make sure everyone understands destructive interference. Think of it like noise-canceling headphones.
Good example.
When the microphone on the headphones picks up the sound wave of an airplane engine, the headphones instantly generate a sound wave that is the exact opposite, the exact inverse of the engine noise. When those two waves hit each other, the crest of one fills the trough of the other, and they cancel out to zero. Silence.
Yes.
So Shor's algorithm creates a mathematical environment where all the universes calculating the wrong answers essentially generate inverse waves of each other, silencing themselves.
That is a superb analogy, yes. The wrong answers cancel each other out, just like the waves canceling each other to make point X go dark in the force-lit experiment.
Yeah.
Meanwhile, the computational paths leading to the correct answer are designed to interfere constructively. Their ways align crest to crest. They amplify each other. So when you finally measure the quantum computer at the end of the operation, all wrong answers have vanished into darkness, and the only result that remains brightly amplified in our universe is the correct answer.
It is absolutely staggering. When you really grasp what is happening, it proves that computation isn't just a clever human invention, like a wheel or a steam engine.
No, it is not.
Computation is a fundamental structural property of the multiverse. The parallel universes are constantly interacting, processing information, resolving paths, and computing reality. We are just finally learning how to write the code to hitch a ride on the great computation that is already happening all around us.
If we connect this back to the broader thesis of Deutsch's book, it perfectly validates the theory of computation as one of our 4 foundational strands.
Also,
The physical laws of the universe allow for the construction of a universal quantum computer, which implies that the laws of physics allow for the rendering and simulation of any physically possible environment. Computation is not an artificial layer on top of physics. It is baked deeply into the very fabric of reality.
so we have the multiverse providing the hardware and computation providing the processing power. What does this all mean for us? If the multiverse is a vast, universe-spanning quantum computer, what is the ultimate program running on it? What is it actually computing?
Which brings us to our 4th and final strand.
The cosmic significance of life and the theory of evolution.
Historically, the progress of science has served to move humanity further and further away from feeling significant in the grand scheme of things.
Yeah, we used to think we were the center of everything.
In antiquity, we believed the Earth was the literal center of the universe. Then Copernicus and Galileo proved we revolve around the sun. Then astronomers discovered the sun is just an average, unremarkable star located on the outer suburban edge of a totally unremarkable galaxy, which is just one of hundreds of billions of galaxies scattered across a freezing void.
I have to quote the late Stephen Hawking here, because he had a quote that perfectly, somewhat depressingly, captures that modern feeling of cosmic insignificance.
I know the quote you mean.
He once said that humans are just a chemical scum on a moderate-sized planet orbiting around a very average star in the outer suburb of one among 100 billion galaxies.
From a purely reductionist standpoint, if you are measuring significance purely by mass, volume, or energy output, Hawking's assessment is entirely correct.
If a rogue solar flare wiped out the entire Earth tomorrow, the sun wouldn't even notice the gravitational difference.
The galaxy certainly would not care. In the grand ledger of cosmic mass, humanity is a microscopic rounding error.
But Deutsch aggressively pushes back against this bleak view, and he uses his framework of the four strands to completely rationally redefine what makes something significant in the universe.
Yes. He argues that life, at its most fundamental level, isn't defined by movement or breathing or even having a heartbeat. If you look closely at the mechanics of biology, life is fundamentally about knowledge.
Knowledge, okay.
Life is based on the replication of molecules, which we call genes. And genes are essentially lines of code. They are computer programs.
Programs that encode specific, hard-won knowledge about how to survive and extract energy in a specific environment.
Precisely. An entity is biologically adapted to its niche if it embodies knowledge that causes that niche to keep that knowledge in existence.
So, like a bear.
Yes. A gene that instructs a bear's body to grow thick fur embodies deep physical knowledge about the freezing climate it lives in. It is a physical manifestation of environmental data.
But even if genes are knowledge, is that knowledge actually significant on a cosmic scale? Does a bear's fur rival the astrophysical power of a supernova?
To see the true power, consider the impact of human knowledge, what the evolutionary biologist Richard Dawkins calls memes, or replicating ideas.
Abstract knowledge.
Humans, utilizing abstract knowledge, have moved millions of tons of rock and earth to build the Great Wall of China. We have fundamentally altered the chemical composition of the atmosphere of our planet.
And we currently possess the physical knowledge to deflect incoming asteroids or to split atoms to generate massive energy.
Ideas, abstract, weightless knowledge, have physically transformed the surface of the Earth in ways that rival the power of tectonic plates or volcanic eruptions.
And it's not just humans. Plants did it too. The entire oxygen-rich atmosphere of our planet, which changed the color of the sky, was created by replicating genes in ancient cyanobacteria. Life alters planets.
It does.
But here's where it gets really interesting. This is my absolute favorite concept in the entire book. If we want to see the true, objective, undeniable physical difference between living matter and non-living matter, we can't just look at it isolated in our one single universe.
We have to zoom out and look at it across the expanse of the multiverse.
The ultimate multiverse view.
Let us examine the DNA of that bear we mentioned. Imagine looking closely at a specific sequence of the bear's DNA, say a chain 10 molecules long.
Looking close.
Let's assume this specific sequence is a highly adapted gene. It contains vital survival knowledge for the bear's heart function. Right next to it on the strand is a sequence of what biologists call junk DNA.
Junk DNA.
This is a random sequence that does absolutely nothing, embodies zero knowledge, but just gets blindly copied along with the rest of the strand.
Now, in our single universe, if you isolate those two sequences and look at them under a powerful electron microscope, they look completely identical. They're just two strings of chemical bases.
By purely looking at the local physics and chemistry, you cannot tell which one embodies the life knowledge and which one is just random junk.
But now, let us shift our perspective. Let us utilize the framework we have built and look at those same two microscopic sequences across millions of nearby parallel universes.
Throughout evolutionary history, DNA is constantly subjected to random mutations. Perhaps a highly energetic cosmic ray from a distant exploded star strikes the DNA molecule, altering a single chemical letter.
But a cosmic ray is a quantum entity. It behaves quantum mechanically. It travels in slightly different directions in different parallel universes.
Therefore, it causes completely different random mutations in the bear's DNA in different universes.
Okay, let's track the sequence of junk DNA first, because it doesn't do anything. It doesn't matter if it mutates. The bear survives anyway, has cubs, and passes it on.
So over millions of years, across millions of universes, that junk DNA mutates wildly in every direction.
In universe A, it's one sequence. In universe B, it's totally different. In universe C, it's something else. If you look at that spot of DNA across the multiverse, it is a chaotic, random, unstructured mess.
But what happens when we look at the adapted gene across the multiverse?
The heart gene.
Because that gene contains vital survival knowledge, how to build a functioning heart, if it mutates significantly, the resulting bear is born with a defective heart. The bear dies before it can reproduce.
So that mutated gene is not passed on to the next generation.
Oh, wow. So in literally any universe where that specific vital gene mutates, the lineage ends right there.
Which means, by process of elimination, in all the millions of universes where the bear lineage does survive and exists today, that specific adapted gene must be exactly perfectly the same.
Precisely. Because it contains objective functional knowledge, it fiercely resists variation. If you look at the adapted gene across millions of parallel universes, it is perfectly identical.
It forms a massive, regular, identical physical structure cutting across the multiverse.
Yeah.
It is like a rigid crystal spanning across parallel dimensions.
That is the beautiful, undeniable realization. Knowledge-bearing matter is physically distinct and special. Within the confines of one single universe, it looks like a random string of chemicals.
But when viewed across the multiverse, it possesses a rigid, regular, trans-universe structure. Life is the only physical process we know of that creates this kind of trans-universe architecture.
So Stephen Hawking had it completely backward. We aren't just an irrelevant chemical scum on a rock. Think about the vast, empty voids of space, the chaotic, swirling nebulae, the burning stars.
Across the multiverse, they are completely irregular and chaotic. A star might be burning brightly here in our universe, but slightly over to the left in another universe, or never having formed at all in a third.
But wherever there is life, wherever there is knowledge, the multiverse locks into a rigid, identical, highly ordered structure.
Therefore, life is not a localized, irrelevant chemical anomaly. Life is a fundamental, astrophysically significant force. It is the primary process by which the multiverse structures and orders itself.
Looking forward, the ultimate physical future of the universe will not be determined purely by the blind forces of gravity and thermodynamics.
If life survives and continues to create ever more complex knowledge, the future of the physical universe will be determined by the choices, the theories, and the knowledge of living beings.
That is incredible. It completely flips the script on human existence and our place in the cosmos. It elevates consciousness from an accident to a fundamental pillar of reality.
Which brings us to our final synthesis. We set out at the beginning of this deep dive to explore how David Deutsch weaves these four disparate strands together into a unified whole.
Right. Let's trace the braid one last time to see how it all connects.
We began with quantum physics. By refusing to ignore the anomalous behavior of shadows and light, the interference forced us to rationally accept that physical reality is a vast, parallel multiverse.
Then we looked at the theory of computation. The reality of the quantum computer shows us that this multiverse isn't just sitting there static. It is actively interacting, processing immense amounts of information, and solving intractable mathematical problems through the physics of interference.
Next, epistemology. The theory of knowledge. We learned that the engine of progress isn't about predicting the future through blind induction. It is about creating deep explanations that solve problems. Knowledge is created through a continuous process of bold variation and rigorous criticism.
And finally, the theory of evolution. Evolution is the physical, biological manifestation of that knowledge creation process. It is the program that crystallizes functional knowledge across parallel universes, giving life a fundamental architectural role in shaping the fabric of reality.
When you view these four strands together, they cease to be separate disciplines. They form a single, deeply coherent picture of reality. The laws of physics allow for universal computation.
That computational capacity allows for the rendering of complex environments. Our brains and our replicating genes are essentially knowledge generators, and the knowledge they generate physically shapes and orders the multiverse.
The universe isn't a cold, dark, pointless machine ticking down to heat death. The laws of physics actually mandate their own comprehensibility.
Through us and through any other life out there, we are the universe actively rendering, computing, and understanding itself. The true theory of everything isn't just an impenetrable math equation for quarks. It's the beautiful realization that explanation, computation, and life are baked into the very foundational fabric of reality.
It completely replaces the cynical, reductionist pragmatism of modern science with a worldview that is deeply integrated, intensely optimistic, and profoundly meaningful.
So to you listening right now, let's leave you with a final thought to mull over as you go about your day.
If knowledge is the only physical thing that bridges the gap between parallel universes, stabilizing reality like a rigid crystal across the vastness of the multiverse.
What does that mean for the unique ideas, the theories, and the knowledge that you are choosing to create, learn, and share today? By thinking deeply and solving problems, are you building a physical structure of knowledge that literally echoes across a million Earths?
Think about that the next time you happen to be in a dark room and you switch on a flashlight and you watch the slightly blurry edge of a shadow dance against the wall.
Let it serve as a reminder that you are standing in the presence of trillions of unseen realities, all participating in the great computation.
Thanks for diving deep with us today.